Good morning, everybody, or good afternoon, or good evening, or wherever you are in the time zone seeing this video, or, well, here we know it's in the afternoon in Berlin. Welcome, everybody, in crazy times. Part of these crazy times are coroutines, of course, and let's talk about it. May I introduce myself? I'm Nico Josuttis. I'm involved in C++ for a couple of times, written a couple of books, so it's partially all my fault, but there were 200 other people who also were involved in standardizing C++, and it's now a full-time task to document C++. Every new version, every 3 years, we have a new version. So the latest one for me, which means I'm writing about, I'm teaching it, is C++ 23. And 23 is now available good enough in different compilers so that we can use it in practice. And that means we can use, in a very easy way, coroutines, because coroutines were introduced in C++ 20, but now in C++ 23, we are introduced a type called std generator, and that type changes a lot because it makes it very easy to write a particular kind of coroutines. And that's what this talk is about. Most of us are mainly used to the way of programming, paradigm of programming, what we call functions. So you have a data flow, and you are in your data flow, statement after statement, doing something, and one of that might be you call a function. And by calling that function, in the past this was so-called a procedure, you jump to a different place in your program, in the executable code, and you execute the statements that are written there. And at the end, you come back. Everything that was used in the function locally is destroyed. The stack is unwinded, and we go back to where we came from. We might use later on the same function again, maybe with different parameters. Of course, we can use a lot of other functions. Functions can have very different flavors, from member functions to very big global functions, static functions, functions that are operators and lambdas, and so on. But that's only one idea of jumping into some different path of execution temporarily. So there's a different approach, and that approach was coined 70 years ago, which is coroutines were invented, well, at least the term was invented, and the term came from Mel Conway. That's the same guy who invented the term Conway's law, or where Conway's law came from. And that, a coroutine, is a function where you can, in the middle of the function, without ending it, suspend the function and resume it later on. So you call a coroutine, and the coroutine is starting to run, but it's not done yet. At a certain point, we suspend the coroutine, and we come back to the calling side, and then the original function continues and does something until, by the data flow, we resume the coroutine. So we don't have ended the coroutine. The coroutine is still there. The coroutine still has its state with local variables. They are all still there, and we just continue the coroutine just where we have left it. And then we continue until we might suspend it again, and we might come back to where we have resumed it, and then the resumption can again continue and call the coroutine again, and then we might, as in this picture, end the coroutine, run until the end of the coroutine. And we come back. So this is a general principle of coroutines. And a very general picture of coroutines, it's you call functions which you can suspend and later on resume. We don't say anything particular how we resume it, where we resume it. It could be resumed in a different thread. It could be resumed by some other function than the original function. And also, we can have multiple coroutines running. So the important part here is just the coroutine does not run in a separate thread. It runs in the same thread. And the thread execution switches back and forth from the original function and sequential processing of something, and then the coroutine processing. We play ping pong between two functions or even more. Of course, it's allowed, like with each and every other function, that a coroutine might run in a different thread, or that the call and the resumption happen in different threads, but that's orthogonal to the question how we switch back and forth between coroutines. All what counts is that a coroutine is a function that can be interrupted and later on, well, suspended, as we say, and later on resumed. And that opens the hole for a couple of interesting use cases and makes some programming easier. Please note, the idea was coined in 1958. We didn't have an idea of multi-threading yet in these days. So that was, for example, one way to say, let's switch back and forth between two processings of execution. So we could have round-robin processing of the functional behavior on the left-hand side, and then the coroutine behavior on the right-hand side. And of course, we might have even more coroutines and switch back and forth with one CPU, with one thread between these different behaviors. So dealing with the coroutine is not so easy in a programming language. One of the main reasons is you have to keep the state of the coroutine from suspension until it gets resumed. So the obvious question is, where is the state stored? And here you can see, somehow magically this happens. But of course, nothing happens magically in compilers and in execution platforms. So we have to start somewhere. And it cannot, in general, it cannot be the stack, because the stack would be unwinded after we leave the coroutine with the first suspension. That cannot be the way we handle that. So we have to do it in a different way. And just to tell you one thing here, so C++ coroutines, by default, allocate their state on the heap memory. So let's see. That's a general idea we have. So let's see how this is used in C++. And many programming languages support coroutines now. C++, as usual, has the approach, we should be able to do everything you could do with a coroutine. And so there should not be any restrictions. So we came up with a general broad approach to deal with them. And that support needs, first of all, compiler support, platform support, but then also a couple of libraries that deal with the usual use cases. So in C++20, we introduced low-level support for coroutines. That low-level support just is the base of we can use coroutines in C++. There's a way to do that. That piece of code, that behavior has to be supported by the compiler directly. So it's a language feature, not a library feature. And we introduced 3 keywords for that: co-await, co-yield, and co-return, which serve a couple of purposes. First of all, with that keywords, you automatically have a coroutine, and then you can, with these keywords, you can suspend or end a coroutine. And then we have a couple of customization points that are usable in C++, and how you can exactly specify how coroutines are handled, and of course, a couple of utility functions. But just the basics. And you needed in C++20 a lot of boilerplate code to use that in practice. So we knew that. It was never the goal to have full coroutine support, easy full coroutine support in C++20. We knew we need the basis, and then we find out how to deal with that basics, with these basics in practice, and come up later with more support. That was always the plan. And the first step of this plan was to come up with easy ways for simple use cases dealing with coroutines. And the one thing we are talking about is the way that C++23 provides by providing a type called std generator. And that's what we talk about now and how to use it right. Let's look into real source code. So here you see an ordinary function that is, iterating over a loop of elements in an array and printing it out. So we initialize, when the function starts, we initialize an array, and then the next step is we initialize an int, an index, and then while we are less than the size of the collection, we enter the body of this function. And the body of this function is we print out the value in the array with the corresponding index. So first value printed out here is tick. OK, we continue this loop with ++, and that means we come to the next element, we print out tuck. The next time we have the output statement. And the same way, we print the third element of this array, which is toe. And that's the end of the loop, because when we increment I again, we are no longer below the size of this collection, so we leave this function. And that's the end of this function. Now let's convert that to a coroutine. Here it is. You don't see many changes, especially you know where in the code, only in the comment, see that this is a coroutine in big letters or something like that. You just see that in the body of the function was a change, and there's a return type now. Let's start with the body. The body is one of these keywords we have, and this keyword says suspend with the next value. It's yield a value, and when we yield that value, that will suspend the coroutine. And so the code, the data flow you see on the right is slightly changed. Instead of printing the next element in the array, we suspend the coroutine and yield this value to the caller of the coroutine. That's enough to have a coroutine. A coroutine is introduced by having a keyword in the body. It's not because we have a different return type. The return type doesn't matter for the question whether or not we have a coroutine. The only thing that matters is that you have used one of the core keywords in the body of the function. And, but as a consequence, you might have to change something, and that is you might have to introduce a return value. And you see a return value without a return statement. And that's a consequence of being a coroutine. The consequence of being a coroutine is that we need something to deal with this coroutine later on. So in practice, where and how do we get the yielded values? That's a question. And the other question is, how can we resume the coroutine later? And for both, you need what we call a coroutine interface. So we have two things here. We have a keyword, making it a coroutine, and we have a coroutine interface return type, and that interface is responsible for dealing with the coroutine. It's also a customization point for the compiler. Inside these objects, you can configure a few things about coroutines. For example, how to deal with exceptions when they happen inside the coroutine. So the big, that's all C++20. You can see it on the top right of the slide. This is code that so far works in C++20. The only problem in C++20 is you have to write this coroutine interface type, and you need, I don't know, something like between 20 and 100 lines of code to write that. And again, that was the plan, because the typical coroutine interface classes we can add them later by using the C++ standard library. And so far, so good. So we learned a few things with C++20 and introduced in C++20 the first coroutine interface type that is part of the C++ standard. And that's std generator. std generator is a standard coroutine interface type, and the type is specific for coroutines that generate values. And it's a function template, or no, excuse me, a class template, and the type of the class template, which you specify here, is the type of the things we yield. Please note that the type of the things we yield here is not the type we yield inside the coroutine, because it's an array of string literals. So the std array internally holds const char pointers, and these are converted to what is really yielded to the outside, to the caller, which is an std string. So implicit conversion is supported. Okay, and that's it. That's your coroutine. That's a way to say, oh, I have written something I can suspend. Each time I yield a value, this code is suspended until somebody tells us how to resume it. So now it's time to look at the other side of this generator. This is the calling and steering side of this generator, and that is, let's put the coroutine on top of this slide, and now let's see the body, in the body, how we can call this. And the surprising way to do that is a very familiar way in C++. We have something that generates values, and how do we deal with something that has multiple values? A sequence of values in C++ is always a range we can iterate over. And the surprising API of the usability, the API generators provide for users, for application programmers, is you can use the API of ranges. In fact, an std generator is a range. It's even a view, so it's a pretty cheap range to copy. And you can iterate over the yielded values, which in itself internally creates a loop of getting back a value from a coroutine and then dealing with it. You get it back when it's suspended, and then in the loop, you resume the coroutine again to get the next value. So how is this done? So if we go step by step into what a range-based for loop would do here, it would iterate over this coroutine by initializing the coroutine, then calling begin, initializing end, and then iterate while we are not at the begin towards the end. And whenever we want to access the value, we use the star operation. And when we then want to have the next value, we call plus plus. The usual API we always use as base for iterating over multiple values, whether it is a container, whether it is a view or range, and now whether it is the values generated from a coroutine. So now the key part is what exactly happens here and when does it happen. When you call the coroutine, it looks like a function call. And this coroutine call initializes the coroutine. What this means is the compiler does everything necessary to deal with this other function running in the program somewhere else. I'm close to say in parallel, but it's not in parallel because we don't start a new thread. This is all sequential processing by one thread. So we switch give control to the initialization of some data that is stored somewhere. So the coroutine creates a context where it can run. And in this context, we also have a state. And in the state, we will store all necessary informations which we need throughout the lifetime of the coroutine, especially to have state information passed from suspension to resumption. So this in it's a coroutine. Does it mean it starts to run? No, it does not. At this initialization just creates internal stuff to deal with this coroutine. So we immediately return, and what we give back here is the type that is the return type of the coroutine. So we create here an object, and that object has the return type of the coroutine. So it's a std generator of strings object, what we have here. So that means Gen now has the API of generators. And with this API, we are dealing with this coroutine, which we started here. It is a coroutine because it has a co keyword in the body. Okay, so we can do the usual things. One of the things is we might say, let's, for this object, we can iterate over, let's call begin. So begin means let's get the first value from the coroutine. That starts the coroutine. Once again, we don't switch threads. We just jump with our execution model to the assembler code of the coroutine and start with the statements as written there. So that means we initialize the array, we initialize I, we check whether I is less than the array size, and then we come to the co-yield statement. And that co-yield statement is the suspension point, as we discussed before. So we suspend the coroutine with the current value in the array using this index. So we suspend it with tick converted to an std string. That is returned, that is the moment where the coroutine is suspended. So the control comes back to the calling side. The begin call was blocked until we reached the suspension point. And now we have the return value of the suspension, and that is a coroutine iterator, and that iterator holds the value. It's not the value itself, because when we iterate, we always have the position of the value, an iterator, and then with star we get the value. Because one thing we have to check, are we at the end? Did we get anything back? So we initialize the same way an end iterator, and then we do the usual things as we do in the loop. So we check, are we at the end with the count position, with the count iterator? If not, we have a value that was yielded. And with star, we go to that value. And in this case, we take the value and print it out. Okay, that's it. We are back in our thread, jumping back from the coroutine execution in its own context, with its own state, back to the execution context of the function that controls or called the coroutine. And there we continue, and we continue on one thing we can do. We can call plus plus. Plus plus means let's go to the next value when we iterate over collections. So like begin, let's go to the first value. Now let's go to the next value. And that means we give back control to the coroutine, or in other words, plus plus resumes the coroutine. And we continue exactly where we have been. We have been with the co-yield statement in the body of the for loop. And now we do the next statement, which is the reinitialization of the for loop. We still have everything available. We have the array available. We have the count state of I available. And that I is incremented. And we check again whether it's still less than size, which is the case. And we enter the body again. And with that, we co-yield the next value, which is, in that case, tuck, which is yielded. Control is given back to the calling side. So again, like with begin, plus plus blocks until the coroutine gives up execution flow by saying, let's suspend or let's end the coroutine. In this case, we suspend it with a value, and that means we check again, are we at the end? If not, let's print out the value. So we print out tech, and the game continues. So we go with plus plus. We try to get the next value from the coroutine. The coroutine continues and until it comes to a suspension point, yielding, in this case, tau. And we come back to the calling side, printing that out, switching to the next element, which means we resume the coroutine, and that will then finally execute the remaining part of the coroutine, which is the end of the loop, or as an end of the body of the loop, we call plus plus I again, and we double check is I less than size, which is no longer the case. So we come to the end of this coroutine. There's nothing left to be done. So that's the end. We come back, and with that end, we would then, now when we get the, when plus plus pos is done, we check the new state of position. It is equal to end, and that means we know that there is no more value in the coroutine. And that's then we can do something else with the main program. That's it. That's all. So a lot of things are hidden here in this code, especially in the SCD generator class. It has something like 200 or 300 lines of code. And but from an application programmer point of view, that's great. You have one function generating values, and another function can deal with the values by iterating over them. That's it. And if you like, you can have multiple coroutines running, can call begin or plus plus for one of them, and then another coroutine use another coroutine and call begin and plus plus for the other one. So each coroutine running has its own state. It's not that there are some static data somewhere stored. Each coroutine running has a state. That state holds the local state of this coroutine, and whenever the coroutine is resumed, that state is used to continue with the coroutine until it ends. You don't have to end. If at a later stage you don't come to the end, you just stop computation, everything will be cleaned and removed, and the state will be removed wherever it is stored, which is by default usually in heap memory. Okay. Let's do something more interesting. Let's use a Fibonacci function, a function that generates Fibonacci numbers, so a sequence of values where the next element is always the sum of the previous two elements. And yeah, let's first write the function. So we start with 1 and 1. Sometimes Fibonacci starts with 0 and 1, but that's just an esoteric question. And so we start with 1 and 1, and you see that we can already say here, these are the two first numbers we yield. So the first two numbers are 1 and 1. You could even write co-yield 1. That's absolutely fine. And to suspend the first time and the second time, you just give this A and B value. And then you write an endless loop. And in that endless loop, yes, a coroutine can run endless. You say the sum is the sum of the previous two values, A and B. And that's a value we yield. And now, after we have processed that value, we prepare the next computation, which means we have to say that now sum and B are the next two A and B values. So with SCD exchange, A gets the value of B, B gets the value of sum, so that then when we enter the loop again, the loop body again, the sum is now the sum of the next two values. That's it. And yes, here's how you can call it. Let's iterate over all 5 Fibonacci numbers. A Fibonacci, a generator is a view, it's a range you can iterate over. You can use it at the beginning of a pipeline of processing. So you could say, for example, let's only take the first 20 elements here. And with that, you get the corresponding output here. Okay. Generators or coroutines in general can, of course, have parameters. So instead of doing this, we could also come up with a Fibonacci function or a generator that says, I have a limit. How many Fibonacci numbers should I create here in this function? So you simply pass an int to say how many elements should be generated so that we don't have an endless loop anymore. It's that after yielding A and B, we have num minus 2 more values to generate, and that's what we do here in the for loop in the bottom part of this Fibonacci function. Everything else is as before. That means we can now call iterate over all Fibonacci numbers, over the first 20 Fibonacci numbers, and print them out just by calling Fibonacci with this parameter. And in case you want to stop somewhere, you might argue, but what if the number is 0 or negative or 1 or 2? How should we deal with that? Well, 2 will work, but 1 will then maybe not do the right thing. You might not see that after the first one you have the end. You can optionally add a statement saying if the number is less than 1, let's immediately co-return. That's a way to end the coroutine. So it's not a return statement because we don't return something. It's in a coroutine, if you return something, it's like you yield something. That co-return could also yield values, but not with the generator. In general, coroutines could do that. With this coroutine, you just say, let's not go to the end of the coroutine. Let's in the middle stop the processing of the coroutine. And we could do that after, well, even before we start or after the first co-yield, we could say, that's it from this coroutine. When programmers see this code, wait a minute. When programmers see code like this and are not used to coroutines, I have been one of them, then they always wonder, so what's the deal? Yeah, nice, looks all makes sense, we can do that, but how can I benefit from that? I can do that already. I can have something that where we start with the first part, yielding 1 and 1, and later on yielding other values. And yeah, well, all I need is, okay, I need a place where I store the state. Yeah, let's introduce a class. And in that class, we have some state variables. And then I switch between different situations, like I'm at the beginning, twice I yield a 1. And then later on, I yield some values. And after a couple of values, I will not yield anything anymore, hoping that nobody calls me. And in a coroutine, you know that there is no more value because the caller can check for end. Now, if you write your own class, this code might look, well, the same if you provide in your class an iterator API, or it might look slightly different. So let's compare this generator code with a simple approach where let's implement that without a coroutine, which I usually give in my trainings as a cast to the people in the room, because they all say, oh, I can do that already. I don't see anything new. But then it turns out that it gets pretty easily a little bit clumsy. Okay, you need something like a class that holds the state of this. So yeah, here in this Fibonacci class, well, which kind of states do we have here? We have the state of num. That's the parameter is in use in the coroutine. Then A and B, of course, initialized by 1. And then we have I that later on comes into play, and even the sum, but maybe we can deal with that locally. Let's see. And that's it. And then you have an initialization. So the initialization passes the initial value of num. So you would do it that way, that you, for example, say, Fibonacci is initialized with a value, and that value is num. Okay, and maybe we take that opportunity to set the runtime integer I to 0. And then we have to do something that simulates resumption. So say, give me the next value or something like that. And so let's do that. Let's compute the next value. But now it gets interesting. You have to say, yeah, well, in each and every case, we increment I. But if in the first two cases we return 1, in the next cases, until we have filled up, given up, or yielded, or returned num elements, we do the thing you see on the left. It's written slightly different, but essentially it's doing the same. And so we return the third to last value. Oh, and now, okay, how does a caller can see that we see end? So we are at the end of the generation of all the values. So you might now need another function. The caller has to double check whether we are at the end, or another trick would be to say, oh, let's return an optional long. And if we are beyond that limit, that's then after we have yielded the last value, return the null opt, so the optional that doesn't hold a value. All is possible, yeah. Different ways to do that. And the API would look like this in this case, but again, we could also use the API of iterators there. And yeah, let's initialize a Fibonacci function code generator with 20, and then while next value gives us a next value, let's print it out. That's it. So it's not exactly the same API, but that way it's not so tricky to get exactly the same API of an STD generator. Now my question here is, which of these codes is more readable? So in which of these parts, left or right side, do you understand the logic of this Fibonacci function? And I mean, it's a rhetorical question. Of course, on the left. And if you say something else, you ruin my talk here. So, but the point is that if you have things like that, you generate things, but you go through different states. That's exactly what we have. We have a state where we generate ones, and then we generate sums, and then we generate nothing. You have, in fact, a state machine. And in fact, coroutines, one application of coroutines is state machines, to convert state machines into some logical flow where you say, instead of going through different states by looking at state variables, let's just process it line by line as we are used with imperative programming, so statement after statement. And for several programmers, that's easier to read, to understand, and to maintain. So the left-hand side is easier to handle than the right-hand side. And you might forget a few things. You might forget initialization. You could also say these different steps are done with different member functions, but then the caller has to make sure that they call them in right order. So it's pretty simple to write code that just generates values and understand the logic that's behind it, the state machine that's behind it. And that's a benefit of coroutines, that it makes it very simple to implement, for STD generator, to implement situations where you generate values in the background or somewhere else, not in the background of a multi-threading sense, just somewhere else we implement the generating of the values, while the use of the generated values is totally decoupled and just an API that iterates over the general values. And that's great. So here's another typical example for coroutines, which is a ConcQueue is used. So we have a queue because we have one process or one thread that is constantly taking in all incoming events, all incoming messages, or something like that. So we store these incoming things. I call this here of type LMT. We store them in a queue with the necessary protection because multiple threads may be used. And so after initialization, we might provide some call like write the next value into the queue, or with and without move semantics, all details. And then now this might be the part of the ConcQueue where we collect data. And then how can we read that data? Well, great opportunity, take a coroutine, a generating coroutine. So say the API to read this code, these elements from the generator is just a reader, and in that reader, we simply see what is the next value in the queue, so we grant access with the queue mutex, see what is the next element, yield it, and then we are done. So, and the ConcQueue then can, in the meantime, with another thread, collect elements while we are processing it from the calling side. Now, and if there is no new element, the reader might wait, might be blocked until there's a new element coming. So the API of the use of the coroutine looks incredibly simple, which is we just, after initializing the ConcQueue, iterate over the reader. And that means we iterate over the values that are already there or come in, and when they are not there yet, we wait here and we are blocked here, and then we process them. And the real good part of this is that in the place where we deal with the incoming values, we don't see anything of the problems of multi-threading, of generating values, etc. So we have completely decoupled the generation of values coming in by different threads from some area, decoupled from the way we use that. And we could have multiple readers and even deal with multiple readers to deal with this queue. That is a benefit of STD generator and coroutines in general. So, STD generator decouples generation of values from their processing. It could be more or less each and every place, each and every function could become a coroutine except main. Main is not allowed to be a coroutine. And then we could, so member functions like have seen and other things. And then we have the fact that the coroutine interface, that the generator class is a coroutine interface class. It, by the way, is a lazy. It is for lazy coroutines. That means initialization does not start the coroutine. The general principle of coroutines in C++ allows also that the initialization already starts the coroutine, but that's not configured inside STD generator. It would have to be configured in the generator type. And then the view of this, the API you can use with the generator to use it is the API of an input range. You can iterate once from begin to end. So begin starts the coroutine until co-yield or the end. ++ continues the coroutine until co-yield or end. And star yields the last value that was yielded before with begin and ++. One more information, coroutine exceptions are propagated. So if inside the coroutine you have an exception, that exception is propagated with begin and ++. So why we are saying give me the next value and we run on an exception, that begin and ++ will rethrow the exception on the calling side, on that called begin and ++. So here's an example. We have a coroutine that has some output, then co-yield 1, then another output, co-yield 2, then another output, co-yield 3, and there, let's simulate, we throw an exception, and let's here have a generator initialized with this coroutine. So we are calling begin, we start the coroutine and getting the first value. This might propagate an exception that's in front of co-yield 1, and then we print it out, and then in a loop we print out the next values, and each ++ might propagate an exception coming from the coroutine. So the first time when we co-yield 2, we don't have an exception. But when we call yield 3, before we do that, we have that exception, and that means the exception is thrown then, and then we catch it here and print out the message. A few things you have to be careful with a few things with coroutines. So far, that's pretty simple. There are a couple of things to remember when using coroutines. And now comes the tricky part, which I can cover slightly. And that is, we have a couple of caveats you have to follow. So please don't iterate more than once. So if you have a coroutine initialized, call once begin to iterate over the values until the end, not further. And don't call begin twice or whatsoever. If you want to iterate again, create another or initialize another coroutine. Please note that otherwise you get runtime errors, and that might be undefined behavior and give you more or less good behavior. Wait with the pictures until the next step, because there's more problems. So don't take parameters by reference. We come to that in a moment. Then yielded values usually have reference semantics and are only valid while the coroutine is suspended. When you resume it again, you should have made your own copy of that value. And then you cannot iterate when the coroutine object is const, and you cannot copy coroutine generator objects. And let's look at a few things. So the most surprising thing is this. Everybody who writes functions is used that instead of passing something by value, I can pass something by reference. That might even apply to int. Might not be useful for ints, but you can do that. So let's here pass to the Fibonacci function a const int reference value. And you see the call passes 20. So to ordinary programmers, this looks pretty safe. So what could go wrong? Because, yeah, we pass 20. We are used to that, to a function, and it just works. The 20 is available in the function we call. That's it. But coroutines are different. Please note that this 20 is not stored in your assembler code. It is the int object is created on the fly because we, in the call, need a reference to it. So we will create the int. 20 is an R value. So we create an L value, an object that has a locatable value when we make this call. And this call then does the initialization of the coroutine. But after the initialization is done, we return from the expression Fibonacci 20, and that means the temporary created int from 20 for 20 is gone. So if then the coroutine starts to run, then later on, and you use this reference, it refers to something that is no longer there. So the referenced object is gone after the initialization of the coroutine. And you can no longer use it later unless you made sure that your reference refers to something that's really available throughout the coroutine. And don't be confused because it looks like in the calling side, the 20 is in the scope of the range-based for loop, and that 20 should be available the whole time. That's not right. In the range-based for loop, we have fixed it that every temporary object that is returned and used is available, but this 20 is gone. And this code crashes. Yes, it crashes, or does something strange, depending on whether you need the value or use the value somewhere or not. So look at that. I have here the example, Fibonacci 20. Everything is good so far because accidentally, while the coroutine is running, the memory where we stored the object with the 20 was not in reuse. So let me just, for some fun, enable another Fibonacci call. Well, the important thing is we have to create something on the stack where this object is stored. And you see our initial Fibonacci function is no longer running up to 20 values. And if you use that value, of course, it might be more severe. So here it's only the number, the times we run this function. If you pass something by reference that's local from the calling side, something significantly worse can happen. So that's it. Yeah, don't declare std generator parameters by reference, or ensure that the referenced objects exist throughout the whole lifetime of the coroutine. So because the coroutine internally creates a state for everything available, but that does not mean it creates a copy of num. It creates a copy of the reference. That's the point. The other point is that generators cannot be used when they are const. So let's write a simple print function, a generic print function that we can use to print all elements which we pass as a range to this function. Please note the coroutine is passed here by reference, by const reference, because we only read. Well, that's a mistake we already learned with views, because due to a severe design mistake in views, we have the situation that even some views require that you cannot iterate when it's const. But in generator, this is kind of necessary, because we say that a begin does something severe with the state of the generator. And that means begin is not a reading call. And the range-based for loop into this print function, calls begin, and that cannot work, cannot compile on a coroutine. Begin is only supported when the coroutine generator class or object is not const. So just calling print for our Fibonacci function is not compiling. Well, it's at least not a runtime error, great. And so what do you have to do? Well, one of the possible solutions is to use universal references. Universal references are references that refer to even to temporary objects, like here the Fibonacci 10 initialized generator, without making it const. But we still don't copy it, because copying would also not be allowed for an std generator. The copy is disabled. So that way it works, and we can iterate over the elements. This is a print fix you also need for some of the views. So yeah, welcome in the game. It seems that the times where we declared objects by const l-value reference are over now, thanks to these new technologies. Yeah, and the other way, if you have it, you might call it again, even with a move. That's also possible. But please note that if you do that, you would do two iterations, so that's undefined behavior. Don't do that. Okay, these are the two most important things you definitely have to know when you start to use std generators, because these are traps you fall immediately in. There are a few other things to know and to deal with when you use generators. So first of all, maybe a little bit surprising, generators can yield references. So that is a little bit funny. It's so that if generators yield values, it's not a big deal. If the value co-yields is a temporary object, an R value, then you even, from the calling side, you get access to the original object. It's not even moved. It's the original object. If it's an L value, it's copied. And which is usually fine from performance perspective. But you can change that. You can declare the generated types to be references. And if these references are not const, you can even pass back data to the coroutine. And on resumption, I'm not sure this is good to do, but I never learned, when I learned something in my life, there's nothing in C++ weird or so weird enough where you don't find a useful use case for that. So that way you could use a generator so that when you suspended the coroutine, that the resumption gives something back to influence further processing. That is in principle possible to implement with generators. Then the next thing is there's special support for that generators can delegate the work to sub-generators. There's a special functions for that. The point is, by default, you would co-yield a whole generator, but you might co-yield all the values from a sub-generator. And for that, there's a function called std ranges elements of. And then finally, you can influence the way generators allocate memory. And that is, you have, by default, it is stored in heap memory. Theoretically, that can be optimized the way that it's on the stack, but only in very rare cases this can happen. So in principle, please assume that the coroutine state is stored in memory, but with the PMR technique introduced in C++ 17, you can specify your own allocator, and with that own allocator, when that is a return type, if you have a PMR generator as a return type of a coroutine, that way you can specify that the allocation of the state of the coroutine is handled differently. And yeah, that's maybe the most important information, at least the most important I have so far. I have not completely documented that yet in my upcoming C++ 23 book, but there will be, all of these things will be described there. So this is the advertisement block and part of this talk. Yeah, and if you wonder when the book is out, the first draft hopefully will come out this winter. So, and the contents will then be views and generator, and then other things from C++ 23 will be covered, and hopefully in September next year, the book will be done. But everybody who gets an e-version at the beginning for a reduced price will get the updates for free. Good, that's it. Summary. std generator is a coroutine supporting interface type that allows to decouple generation of values from their processing. It's a coroutine interface class. It's for lazy coroutines, so that not immediately start. To start, you have to call begin, and that generates values. So inside, you either co-yield elements of a type, or you end it with co-return, or by reaching the end of the coroutine. You can specify the type that is co-yielded there, and of course, if the type is a variant or something like that, you could also co-yield different values of different types. And then from the user point of view, it's an input range, so you can iterate once from begin to end, or once onwards until you either reach the end or give up. And you have seen the caveats we have discussed, or partially even seen as an effect in this talk. That's it. That's all about coroutines I have to say now, and I learned now. If you have anything to correct, send me an email. I'm happy to learn still. And then feel free to do something and enjoy life and make the world better and come up with more components that support useful applications of coroutines in C++ in the future. Thank you very much. Some questions? One or 2 minutes. So if there are 1 or 2 questions, go to the mic.
So we have a question from online. As it looks like we get contracts in C++ 26, will it then be possible to have post conditions on co-yield?
I have no idea, but I would assume yes. No, maybe. Ask the contract experts.
Yeah, as an active member of SG21, actually I can't remember if we wound up with support for contracts on coroutines in 26. There were discussions about that, but there is an issue there that right now is probably irrelevant, but the interesting thing is that if you have a const parameter passed by value to the coroutine, to a coroutine, that's the only case in the language where a const object will be moved from. And that creates issues for post conditions.
Okay, yeah, I have a slide where I double-check all the different ways when I co-yield values and how this is dependent from the way you declare your return value. And I forgot there's also support if the value you return and you want later access is a proxy type, there's also special support. And yeah, there are some tricky rules. I'm pretty sure we have that. So ask this guy for all the details. I just explained the basics.
Either now or on Saturday.
Thank you, by the way. Yeah.
Is it possible to yield from a recursive function? Like, could I do a depth-first traversal of a tree and yield during the traversal?
I would say yes. Well, in principle, coroutines can call coroutines. So you might need elements of. So that is it. So because what, I guess so. So good. That's a good question for the book. I take it. And we'll answer it later on.
Thanks.
So thank you very much. Enjoy the conference and see you more next year.